class, welcome to the 1.48 example video. So we are first going to look at number 10. I am going to take my time with these because there's some little algebra things that we need to make sure to clear up for you. And so again, I say it's not the calculus, it's the algebra. So let's take a look. I'm doing number 10 from the text as an example. So let's take a look. Number 10, they are asking for the limit as x approaches 2 from the right, and the function is 2 minus x over x squared minus 4. Okay, so it doesn't matter that we are just checking a one-sided limit for 2. When we are presented with a limit, the first thing we can do is use direct substitution.
Just say hi, Mr. Squirrel. There we go. Okay,
hi,
back.
Mr. Squirrel.
Back to, all right.
So the first thing we try is direct substitution. The reason for that is if I were just checking the limit as x approaches 2, that would bring in approaching 2 from the left and the right. So it must be, if I'm just approaching from the right, I can still use direct substitution. Okay, so let's try it. When I put a 2 into the numerator, I get a 0. When I put a 2 into the denominator, I get a denominator of 0. I cannot use direct substitution. So we're going to use some of the techniques we learned in section 1.3 to see if we can write a simpler function and unveil a limit if there is one. So let's take a look. The limit as x approaches 2 from the right. I don't really see any math right now I can do in the denominator, but I do numerator, but I do know that the denominator is the difference of squares, and it's actually quadratic too, by the way, class. So I know how to factor it. So when you look in the numerator and denominator here, I can almost cancel. These two terms are almost the same, except in the numerator the 2 is positive and the x is negative, and we have the opposite signs here. No problem, let's fix it. Would you agree with me? I can hear you agreeing with me that 2 minus x is the same thing as, I'm going to factor out a -1 and put x minus 2. Let's take a look. Is my x still negative when I distribute the -1? Yes. Is my 2 still positive? Yes, it is when I distribute the -1. There we go. So this expression is the same. I feel like we could use some different colors for the canceling. Let's do that. Let's cancel. Now let's see if we can use direct substitution to unveil a limit. Notice there's just a -1 in the numerator, and in the denominator, I can now pop that 2 in and I get a 4, and there is your limit. If you graphed this function on the graphing calculator and approached an x value of 2 from the right, you would see that the function value is approaching a -1/4. Okay. We're going to do one like 11 because it's important. It's really important. But there's not really another one like it in this section. So I'm going to do a problem like 11. And let's see what they're asking us for. Let's do the limit as x approaches. We're going to do -4 from the left. And the value of the function is going to be x over the square root of x squared minus 16. Okay, let's try direct substitution, right? In the numerator, sure, I can put a -4 there. From the left, that's okay. Take a look. Of course, when I try to put a negative...
Square root of 0.
Yep, square root of 0, can't have that. Can I simplify this function in any way? Okay. The reason why I have this up is students will tend to think that they can simplify this function. All right, I am going to simplify this function in the denominator incorrectly. X minus 4. Class, is that okay to do? Is it okay for me to take the square root of x squared and call that an x? Is it okay for me to take the square root of 16 and call it a 4 and put a minus sign? Is this the same? No, it actually is not. And what's one way I could tell that? I could tell that by actually putting an x value in here. Let's pick an x value. Let's put in 10. And so let's make x equals 10. And when I square it, that's 100 minus 16. And I have the square root of 84. Okay, well, if this expression is exactly the same when I put a 10 in, shouldn't I get the square root of 84? No, I do not. 10 minus 4 is 6. These are not the same. This is illegal math. I would arrest you if I could. I'm just teasing. I wouldn't do that. I would arrest you, but I would feed you like candy and things. And we would laugh and tell jokes and stuff. Okay, so the square root then, let's go back, of x squared minus 16 is actually, you may say, well, okay, isn't that though x squared minus 16 the difference of squares? X minus 4, x plus 4? It sure is. Plus 4. That's another reason why I can't take the square root. You can take the square root perfectly of something being squared. I don't have two things multiplying themselves here. So what does this mean? This means that sometimes you can't simplify an expression, right? So what's happening here is there's no limit. I can't make one happen when it doesn't. But here's my question for you. Let's go back to the original problem. How come the limit doesn't exist? Dividing by 0 makes something approach infinity or negative infinity. And so let's just give a reason why there's no limit. Is this expression here approaching a positive infinity or a negative infinity as x approaches negative 4 from the left? It's actually easier than you think. Take a look here, class. When you put a negative 4 into the numerator, you get a negative out, right? The numerator's negative. There we go. In the denominator, is it possible to have a negative value in the denominator? Can you take the square root of a number here and get a negative answer? No, you cannot. This denominator must be positive. And so a negative divided by a positive is a negative. So there's no limit, and the reason is this function is approaching a function value of negative infinity from the left of negative 4. So you cannot make a limit occur when one does not. And we certainly tried really hard to find one. Okay, so yay for you for trying so hard. Let's try number 18. All right, what's going on number 18? On number 18, I chose that because, as I promised you, piecewise functions are everywhere. This is going to take me just a little bit to write. Are you laughing?
You're starting to go downhill there.
Oh, I'm going downhill. Thanks for the commentary, Bill. Thank you so much. So they are asking for the limit as x approaches 2. And so of this piecewise function. So notice you have this quadratic for x less than 2. And you have this quadratic for x greater than or equal to 2. And so what do we do here? We do what we always do. We try direct substitution first because x less than 2 is we are approaching 2 from the left, right? The numbers that are less than 2 are on the left. X greater than or equal to 2, we are approaching 2 from the right. And so let's try direct substitution from the left of 2, direct substitution from the right of 2. And if we have the same limit, then the limit exists. If we do not get the same limit, then it does not exist. So let's do a little bit of math here. Let's put a 2 into the top function right here. Well, I guess we don't put it into 6. Let's see, this would be a 4 plus 6 is 10 minus 8 would be a 2. Is the value of the function is approaching 2. Let's put in a 2 into the bottom function here. Let's see, that would be a negative 4 minus 2. We're now at a negative 6 plus 8, 2. There we go. So this piecewise function did provide an opportunity for a limit not to exist, but when we checked approaching 2 from the left and 2 from the right, the functions were approaching the same value, and so the limit, in fact, is 2. Again, lots of piecewise functions in this section. Let's look at 32. In case you're wondering when the torture is going to be done, right? If you notice up here, we have 2 more left. Number 32. Oh, okay, people. Hang out with me here. This is going to take a little bit. Number 32. All right, but that's what I'm here for. Here's the function they give you. This looks crazy. Here we go. So we're going to need a little explanation here, right here at this square root. Are you looking at animals?
He's stretching.
Aw, how cute.
Okay, sorry.
No, that's okay. Okay. Now, one of the things I have in blue is you have to be careful because they ask you all kinds of questions in this section. They ask you for a one-sided limit. They ask you for a limit in total. We've seen both of those. They ask you about continuity. So you have to be careful about what question they're asking you for. So the question on 32 is discuss the continuity. Discuss the continuity. Well, this sounds kind of open-ended, just discuss. So let's take a look. Now, I'm going to approach this in 2 ways. Most functions, as we talked about, are continuous, either from negative infinity to infinity or on their domain. And notice that we do have a closed interval here, that like we talked about over here. So let's first check the endpoints. Because just like limits, continuity occurs often, so I'm really looking for discontinuities. So let's see if we can find any. A discontinuity would occur if over here, number 1 on the continuity test, that the function value of the function doesn't exist, that I can't find a limit, right? Or if 1 and 2 exist, that they have to equal each other. So let's just look at this point by point, and then I want to talk about this graphically. We have a closed interval from -3 to 3. Let's take a look. Let's check to see if the value of the function exists. When we put in a -3 here, notice we have 9 minus 9 is the square root of 0. Sure, I can do the square root of 0. Okay, let's check the 3. Oh, notice because of the squaring, when you put the 3 in, you get 9 minus 9 again. The square root of 0 is 0. 3 minus 0 is 0. Sure, the value of the functions. How about anything in between -3 and 3? Are there any issues here? Any values where we wouldn't be able to produce any x's of function value? So let's take a look. Let's try right in between. It's 0. A t of 0? No. 9 minus 0 is 9. Square root is 3. 3 minus 3. No, I think any values, any integers, 1, 2, -1, -2 on this interval, I think I can get a function value out here, okay? Now, where is there trouble? Notice that I can't put a 4 in here for t, right? If I put in a 4, that would be 16, 9 minus 16. Now I have a negative number under the square root, and we no longer, right, have continuity. We're now on an imaginary plane. So, according to me, just by taking a look at the first endpoint and the last endpoint and thinking of all the x's in between, that this function has, at every x, does have a function value. Now let's talk about limits. We know that if 3, we know what that function looks like. That's a horizontal line. That limit exists everywhere. Take a look at this square root right here. Square roots are always output a value for any x, right, where this has to be positive underneath, and the square root will output a positive value. So on its domain, a square root is always continuous, and the subtraction of those, of 2 continuous functions, is continuous. Okay, now I do want to talk about this graphically though. I think this is continuous everywhere, is what I'm saying. Now, one other point I want to make here, though, is I know what a function of 3 looks like. What is that function right there? Because if I could draw a picture of this, right, from -3 to 3, I could also check the continuity that way, get a sense of it. Okay, so you may think you don't know what that function is, but you do. let's take a look. Let's just play with this for a little bit. 9 minus t squared. If it's okay with you, I'm just going to use x's instead because it really doesn't matter. Let me go back and put x's in here. Okay. I have this function right here. What does this look like? Let's square both sides to get the square root, to get the, eliminate the square root. There we go. I squared both sides. All right. Let's add an x squared to both sides. There we go. Now, can you tell me, what is this a picture of? I think it looks familiar to you. We talked about it in pre-calculus and you looked at it in geometry. This is a circle with a center at 0, 0 and a radius of 3. That's what this is a picture of. You are going to see this all the time in calculus. And now you'll know when you see it, if there's a 16 here, that it's a circle with a radius of 4, located at 0, 0. But let's take a look at this. First of all, the square root of 9 minus x squared, notice that this expression can only output a positive value. So let's take a look here. Remember, we were stuck in between -3 and 3 here, right? We said this is a circle with radius 3. Certainly looks continuous, doesn't it? Now let's take a look here though. This is only a positive, right? We can only output for any x we put in here, the answer is only going to be positive. So when you have that positive square root, you only have the top half of the circle. Okay, so that is what this function looks like. And certainly if I flip it upside down and move it up 3, it is still continuous from -3 to 3. So just trying to help you get a sense of, really use your internal sense to evaluate when other things like a little algebra might fail you. Okay, last problem. Any questions there, Bill, on that one?
I was trying to follow. I really was.
You probably talk about circles a lot too when you were in the
Not
classroom.
like that.
Not like that. Number 80, last one. Last one, you must all be so excited. Number 80, what did I decide that you need? Oh, I have this picture here. Okay, so I'm just gonna recreate it. Let's see, it looks like this. Okay, this is 0, here's 4, and here's 4 here, and they give this picture. Okay, so it looks something like that. So they gave you this function here, and they even gave you a picture of it, and it's kind of going like that. Here's what they want to know. Describe the intervals on which the function is continuous. So describe where this function is continuous. This is so much easier than you would think. When I take a look at this, all looks continuous right here. Okay, how do I name that? Well, it's never actually hitting 0. There's an asymptote, a vertical asymptote there, which makes sense. Take a look here. You can't put a 0 in to this, right, into this denominator here. So I would say, well, close to 0. So for x greater than 0, right, because it's not touching it, and let me take a look, and it continues on. So that's it. Describe the continuity. This function is continuous for x greater than 0. And that's it. That's it for our examples. I hope you enjoyed our example video.